Hey, Honors Peep, this is Underwood here with another Honors Chemistry webcast. Today we're going to be talking about Hess's Law. Hess's Law states that the total heat energy absorbed or released in a chemical process is the same regardless of whether the process takes place in a single step or in several steps. Now this might not make a lot of sense, so let me help by explaining just a little bit. In chemistry so far, you guys have been looking at chemical equations in sort of a simplistic view. This right here will probably be a chemical equation that you'd see as being familiar. You've got your reactants and you have your products. Well, chemistry is a little bit more complicated than that. I know you're like, how could it get any more complicated than it already is? Well, it does. Anyway, this is more of a summary equation. Okay, this is the overall reaction, and as it turns out, a lot of chemical reactions have several steps that we don't necessarily talk about. And so as you can see below, I've actually broken this summary equation up into three different parts. And these three different things happen, okay, in certain sequence, and this is the summary that sort of tells you exactly what's going, or that gives you a summary of, all right, when I put these reactants together, I get these products. Well, how does that happen? It goes through these steps. But we can use this Hess's Law, this idea, okay, and we can use the constituent reactions to actually calculate the heat energy that is lost or gained in an overall reaction. And so what I'm going to do is I'm going to show you how to make those calculations. I think the best way for me to do this, to teach you how to do this and to make help you become familiar with these problems, is to just simply do a couple for you. So I'm going to walk through how I solve these problems. Okay. So as you can see, we're always going to give you a summary equation. Okay, and then we're going to give you the constituent equations as well, along with their changes in heat energy. Okay. Now, these equations here, they can be manipulated, they can be flipped, they can be multiplied, things can cancel out. You're going to see how that works in a moment. But what our goal is our goal is to combine these three equations and to add these heats of this change in enthalpy to find the total change in enthalpy for the given equation. First thing I do is I want to go through and I want to survey each one of these equations and see how it helps me get to this summary equation. So I'll kind of show you what I do. I walk through. Okay, I see this first equation and I see a carbon. Okay, well there's no carbon up here, so that means this carbon must eventually go away somewhere. We'll find out where that goes in a moment. We've got oxygen on the reactant side. That's good because I've got oxygen on the reactant side here. I've got CO2 on the product side. That's good because I've got CO2 on the product side in my summary reaction. So right now this equation is looking pretty good. It's looking like it's already been manipulated the way it needs to be manipulated. So let's go ahead and move on to the next one. Here you can see we've got a sulfur solid, and if I look at the summary equation, I don't have any sulfur, so that must go somewhere eventually, but we'll find out where that goes here soon. I've got oxygen gas, and that's nice because I've got oxygen gas here on the reactant side, so that's good. But then I've got sulfur dioxide here, and that's neat because I've got sulfur dioxide here on the product side as well. The only problem is, notice I've got 2 molecules of sulfur dioxide here and only 1 molecule of sulfur dioxide here. So what is the solution? What can I do to make sure that I have the correct number of sulfur dioxide molecules? Well, I can actually multiply this entire equation, this whole thing, by 2. So when I do that, I end up with a new equation. I end up with 2 sulfur solid plus 2 oxygen gas molecules. My reaction arrow goes here, and I end up with 2 molecules of SO2 gas. Well, that's pretty convenient, right? Awesome. But remember, if you multiply anything, if you multiply these equations by 2, I have to also multiply my change in enthalpy by 2 as well. So now my new change in heat energy is going to be negative 500. See, 593.6 kilojoules per mole. Now I get in the habit of once I've manipulated an equation how I see fit, I go through and I just cross out the old one. I don't need this one anymore. I've already done what I need to do with that one. So now I've surveyed that, I've manipulated that, I feel good about that. Let's go to the third equation here. Okay, I've got carbon here on the reactant side, and I don't have any carbon here on this side, so it goes somewhere, but we'll find out where that goes eventually. I've got two sulfur solid atoms here. Well, I don't have any sulfur up here, so that goes somewhere. I got to find out where that goes. We'll figure out where that goes eventually. One thing I'm really looking at is I have a carbon disulfide molecule here. And that's kind of neat because I have a carbon disulfide molecule here. The only problem is this one is on the reactant side and this one's on the product side, and I need somehow to get this carbon disulfide molecule on the reactant side. And actually what you can do is you can actually flip this equation. So if I was to flip this equation, now my CS2 is on this side of the equation, and that's pretty neat because now my carbon is on this side of the equation and my two sulfurs are on this side of the equation. Now I have things are starting to line up nicely for me, but the only thing is if I go and if I flip this equation, that means I have to flip the sign of my enthalpy as well. So now my new change in heat of enthalpy is going to be 87.9, but it's going to be negative because I flipped it, kilojoules per mole. Okay, and I'm going to go through, because it's a habit here, I like to go through and make sure that all these that I don't need anymore are canceled out. I've already manipulated these, okay, so I don't need to look at them anymore. I want to make sure I keep everything nice and tidy, okay? So now I take a peek at what I have. Okay, well, as it turns out, elements and molecules that exist on one side of the reaction arrow can cancel out the same element or molecule on the product side. So if I look here, I've got a carbon here, okay, and I can cancel that carbon out because it's on the reactant side, and I can cancel that out with a carbon that's on the product side. Nice. Well, the carbon goes away. Good. I knew that was going to happen eventually. I just didn't know when. And now I look here. I see I've got two sulfur solids, but the sulfur doesn't exist up in this summary equation. So as it turns out, this bad boy is going to go ahead and cancel out this sulfur on this side. Well, that's nice. So now let's look and see what I'm left with. Okay? I am left with oxygen, carbon dioxide, a little bit more oxygen, some sulfur dioxide, and some carbon disulfide here. And so what I can do is I can actually combine all of those things that are left, those things that haven't been canceled out. I can combine them all, and I guess and what you'll see is quite magical. It's going to end up looking just like my summary equation. So here, I start out with my carbon disulfide. I'm going to react that together with, look, 1 molecule of oxygen plus 2 molecules of oxygen equals 3 oxygen molecules, and that's in a gaseous form. And then I look here, I've got my CO2 on the product side. That works out nicely. And I've got my 2 sulfur dioxide molecules on this side. So that's cool. That works out nice. Now, I have my summary equation, so I know that the work I've done is checked. It's good to go. It's awesome. The only thing now I need to do is add all of my enthalpies here, all of my change in heat energy. So I need to take my negative 393.5, I need to add that to my negative 593.6, I need to add that to my 87.9, and what I'm going to get is a new change in enthalpy for this entire equation, and that is negative 1,075 kilojoules per mole. I know, it's a lot. I know, it's your first time checking this out. It's pretty difficult if you don't know what you're doing, but if you keep practicing, it's all going to make sense eventually. So let's go ahead and do